All right, we'll continue on with our Archaean Hadean geology for Chapter 8. So here I want to talk a little about the greenstone belts and the granite gneiss complexes. So during the Archaean time, remember we're making these protocontinents and we're starting to see that Archaean type or A-type subduction with a thicker mafic to ultramafic crust, shallow subduction, higher heat flow, and really melting of that ultramafic or mafic rocks to produce the more felsic. Here they call it granite intrusions, but really there's those TTG, the tonalite, trondhjemite, granodiorite series, and they're eventually making larger continents. So these granite gneiss complexes, they amount to about 90% of the Archaean rocks, and the greenstone belts, which are essentially seem to be like the suture zones or the places where you amalgamated these Archaean island arcs, they account for about 10% of the Archaean rocks. They date from 3.8 to about 2.5 billion years ago, most between 2.5 to 2.7 billion years ago. Again, they're being in place in these island arcs, this early Archaean type subduction. They're high grade, so for metamorphic rocks, grade refers to temperature, so they're high-grade metamorphic rocks, those granite gneiss complexes. And then there's also pods of metamorphic mafic rock, which seem to be almost like in a synclinal folded form in these greenstone belts. And then again, that's our criteria for that A-type subduction. Here's a picture from your textbook showing some of the sequences of these greenstone belts. So we have the granite gneiss complexes, which are the older metamorphosed rocks. Then we have these series of lower volcanic units, probably peridotite or basalt. So remember, peridotite, when it's a volcanic, it's komatiite. Then we have a middle volcanic unit, which is mostly mafic. Then there's sediment eroded from these island arcs. And then we have these granitic intrusive, which are part of that tonalite, trondhjemite, granodiorite sequence. And remember, those are probably being formed by melting, that A-type melting, shallow subduction of this peridotite basalt unit here to give us some more felsic rocks here. Here's an image showing some good pillow lavas, so obviously erupting underwater. And then here is some of those granite gneiss complexes. So here's another picture kind of showing these little protocontinents, how we're start seeing this A-type subduction, and then eventually these coalesce to form a larger continent here. Here's an image from your book showing the same idea, where we have these smaller island arcs, shallow subduction, kind of a thicker crust here, and then only ocean lithosphere, and then the crust is growing by accretion, this continental accretion. So that's how these Archaean Cratons are starting to grow, by this accretion. And remember earlier I talked about this underplating where upwelling magmas pond at the bottom of the crust here and begin to cool and have the crust grow kind of from top down, so they thicken through the underplating process. There's a couple of other ideas regarding the origin of these greenstone belts. One could be this intercontinental rift, where you're breaking up one of these little proto-continents in the Archaean, and that allows this plume of ascending magma, maybe a mantle plume, which results in partial melting of that mafic crust that's there, and producing these less mafic trondhjemites, tonalites, and granodiorites. But also you're seeing these intrusions in this rifting model. Another one could be where you're seeing a subduction here, and then there's rifting behind the volcanic arc here. So this back arc rifting. But in either model, one thing I do want you to understand is this idea about the TTG, or the tonalite, trondhjemite, granodiorite sequence. And because there's such a higher heat flow in the Archaean during this time, instead of getting melts from the mantle, we're partially melting that subducted amphibolite or eclogite. So these two terms refer to metamorphosed rock. So amphibolite usually metamorphosed at a higher temperature, maybe not as deep as eclogite. Eclogite's also a higher temperature, but more pressure. But whenever you see eclogite, for sure, you're thinking about a subduction zone. And amphibolite refers to the metamorphosed mafic rock that's being partially melted to give us these more felsic rocks of the TTG series here. So here's another view of this underplating where we get this thickened mafic crust from underplating, and then we're partially melting that, and it's going to give us the more felsic tonalite, trondhjemite, granodiorite plutons. And then that's kind of thickening and building up our protocontinent. And then other things may happen where, again, the shallow subduction, because this is warm, it's not going to dive down into the mantle. Warm, shallow subduction, A-type subduction, and that's going to maybe will delaminate, cause more mantle upwelling, partial melting of this mafic root of the continent, producing more, even more. Here they have calc-alkaline magmas. So calc-alkaline magmas are usually starting to signify more modern type of subduction. So the types of volcanics and plutonic rocks we see at modern convergent margins are more of this calc-alkaline series. So we're starting to see a change here. Here's an image of these trondhjemite, tonalite, granodiorite intrusives and greenstone belts over here in northwestern Australia. In fact, I have Google Earth here. If we zoom in to this region, we begin to see those plutons or intrusives that are more felsic. So this is an Archaean Craton of western Australia, and you can see, I think they mentioned that this one's about 40 kilometers in diameter. But this is this region of these greenstone belts and then these intrusives. So this is documenting those Archaean Cratons. And what we see is an example of some of those mafic rocks, the basaltic rocks, and even ultramafic rocks, which show this distinctive pillow lava structure, right? So again, erupting into some body of water. Here, komatiites, because you have to melt the mantle, you need at least 1600 degrees centigrade. Today, the mantle, at least the upper mantle, is at around 1200. So we're not seeing anything near these temperatures. Why are they green? They're green because they've been slightly metamorphosed, and they have this amphibole mineral called actinolite. They also have chlorite, which is green, and epidote is an altered feldspar. Now, looking at the atmosphere and the hydrosphere. So the first atmosphere is whatever the solar system had. And the solar system, 4.6 billion years ago, primarily had hydrogen and helium. And that eventually formed the sun. Although any hydrogen and helium that was on Earth just blew away because Earth doesn't have a strong enough gravity to retain hydrogen and helium. So that just vaporized or just went off into space. The next abundant gas is carbon dioxide. And so the early Earth had about maybe 90, 95, 96% carbon dioxide. So dominated by CO2. There was very little to no oxygen. And whatever oxygen was being produced might have been produced by this photochemical dissociation, which can happen in the upper atmosphere. The other thing in terms of the gases, where were they coming from? So outgassing is the release of excess volatiles from the crust or the planet. So there are these gases like water vapor, carbon dioxide, methane, hydrogen sulfide, sulfur dioxide. All those are gases that really don't go into minerals. They just vaporize and they become the atmosphere. And Earth does have a strong enough gravity to retain those gases. So obviously today our atmosphere is very different. We have mostly nitrogen, about 78% nitrogen gas, about 21% oxygen, a little bit of water vapor, and small amounts of ozone and carbon dioxide. So this is kind of showing the idea of this outgassing from volcanic vents, producing the mostly water vapor. That water eventually precipitated and started filling the ocean basins. CO2 gas is the next one. Ammonia gas, methane gas, plus other gases. So these gases condensed to form the early atmosphere. Water and other ions fell to Earth to form the oceans, and eventually we get oceans and atmosphere. Another thing that's important, since there was no free oxygen in the atmosphere was chemically reducing. In other words, the iron that was on land was not rusted because there was no oxygen to rust the iron. And so there are deposits that are Archaean in age of detrital sediments, so being deposited by water, being eroded, weathered, eroded, transported, usually in maybe early streams or shorelines. Any oxygen would have rusted that material. But yet we find pyrite and uraninite, which are easily oxidized, if we find them in a reduced state, they're not oxidized, telling us that there was no oxygen in the atmosphere during this time. we start seeing oxidation of iron in Proterozoic rocks. And so we'll talk about this oxygen revolution and how really photosynthesis started pumping all this oxygen in the atmosphere, and we needed to rust this iron. And worldwide, we find these formations called banded iron formations that document the rusting of this iron. Now let's look at this photochemical dissociation. So it involves ultraviolet radiation in the upper atmosphere, and this could account for about 2% of today's present oxygen, right? So it's kind of the dissociation of the water vapor here. But the one that accounts for most of our oxygen is going to be photosynthesis. So organisms producing a byproduct of oxygen, free oxygen, into the atmosphere. So again, we mentioned that outgassing was probably the main source of water for Earth, just excess volatiles. Although there's been recent work that some of this water, maybe up to even 50% of the water, may have arrived to Earth from comets or icy bodies or asteroids that hit the planet. Again, the early oceanic and continental crust. So remember, in the Archaean, there was very little continental crust, only little protocontinents. The first appearance of oceanic crust was early on, about 4.5 billion years ago, mostly in those komatiite basalt ultramafic rocks, mostly formed at ocean ridges, maybe oceanic plateaus, back arc basins, pretty widespread. Pretty much that's all there was. And remember, we're partially melting the upper mantle to generate these rocks, these mafic and ultramafic rocks. For these protocontinents, these protocontinental rocks that began to form in the Archaean, remember the oldest rocks we have are the Acostan ice at about 4 billion years. Certainly by 3.8, we start seeing some evidence of continents, and that's mostly up down in South Africa, the Pongola group, and the Craton seems to be about that age. So it's first evidence of larger land masses that occurred. And they're forming by this subduction zone. It's mostly that shallow subduction, high heat flow, over thickened subduction of either komatiite or basalt ocean crust. And then that's partially melting, which is in the form of eclogite and actinolite. It's partially melting to form that tonalite, trondhjemite, granodiorite series that eventually forms this more felsic type of rock. Remember, that's local and small in extent. Think about that region of Australia that I just showed you. And then again, we're partially melting those wet mafic rocks, the eclogite, the amphibolite, and maybe even rocks that are maybe more evolved or more differentiated, which are the intermediate andesites. So going back to this Pongola supergroup, so in South Africa, the Craton includes greenstone belts plus larger regions that show evidence of it weathering and erosion and transportation and sedimentation indicative of large continental land masses. And the Witwatersrand covers 40,000 square kilometers. And the sediments there are up to 8 kilometers thick. So Witwatersrand is famous for their gold deposits. About 50% of all the gold that's been mined on Earth comes from this region of South Africa. But the key thing is that by about 3 billion years, we start having continents, larger continents, right? So that's really the main thing I want you to get out of this Craton and Pongola supergroup Witwatersrand sequence, is that we're starting to see pretty big continents by about 3 billion years ago. Remember, before then, they're all small protocontinents. They're accreting and maybe underplating to get bigger over time. And here's a stratigraphic sequence kind of showing this progression of deeper water to continental setting, where you're starting to see ripples along a shoreline, maybe ripple marks in a stream bed, mud cracks, so there's evaporation, some graded beds, more ripple maps. So you go from, basically you're developing a continental margin. So this mid-Archean Pongola supergroup in South Africa, there's volcanism, there's sedimentation, early life development on Earth's oldest stable continental margin. So we just start forming a continental margin